This video will cover section 1.3 of SACE Year 12 Physics, and in particular satellites. This is an excerpt from the SACE outcomes, and you can see what we'll be going through in this video. So in our last video we looked at gravitation, and that's a force between any two objects in the universe. Now when we add motion to that and look at the biggest scale, we can talk about satellite motion. So the definition of a satellite is an object that orbits another body. The smaller body is called the satellite if gravity is the force that provides the centripetal acceleration. So an example of a satellite will be planet around the sun, moon around a planet, or satellites, man-made satellites around the Earth. Due to the gravitational force acting on both objects orbit around each other. Now, in most cases we don't really witness this because one object tends to be a lot larger than the object of the satellite that's orbiting. So the Earth is orbiting around the Sun and the Sun is orbiting around Earth. However, the Sun is just so much bigger, and the center of mass of this two-body system is effectively at the center of the Sun. Let's consider a circular orbit of a satellite, and we can see that we've got the radius here. Notice the radius or the distance between the satellite and the other object is measured from the center of mass of that object to the path. The acceleration is centripetal, meaning it goes towards the center of mass there. So the magnitude of this acceleration, as we learned in previous lessons, is denoted by the velocity squared divided by the distance between. Now, since force is mass times acceleration, we can adjust this formula slightly, so you can see that the acceleration here, if we multiply it by the mass, we get this formula down here. And I don't think this one's on your formula sheet, but it's easy to get to. So we know that the centripetal force is given by mv squared on r, and we also know that this force is due to gravitation, which between two objects is given by this formula here. There. Equating these two formulas, we can find that the velocity of the satellite is only dependent on the mass of the larger object and the distance that the satellite is away. So the mass of the satellite itself, it doesn't matter. So the speed of a satellite in orbit depends on how far away it is from the object that it's orbiting and how long this takes as well. So that's given by this formula here. Now, if we square the formula that we had on the previous slide, we get this one here, and substituting in this value for velocity into this value for velocity in here, we can equate these two sides of the equation, which allows us to determine what the period of orbit is for a satellite based upon the distance away it is and the mass of the object that it's orbiting. Okay, so from that previous equation, what that means is that just for a particular radius of orbit, there is only one possible speed for a stable orbit. So maybe during the formation of the solar system, there would have been thousands of other objects and planets between all the gaps of the major planets that we classify, but they might have been going too fast or too slow, so they either escaped the solar system or it was too slow to keep that stable orbit and collided with the sun over time. Just something interesting, that there's about 4,600 satellites orbiting Earth at the moment, all in different configurations and orbit paths. Now, there are a lot of companies that want to launch more satellites over the next 10-20 years, and their plans might put the number up around an additional 12,000 satellites. So some of these will be used to give Wi-Fi to every location on the planet. That's one of the goals, I think, of Elon Musk's company. Some concerns about putting so many satellites into space is the idea of space junk, and also will all the satellites fit and how do they stop crashing into each other. I won't go into that in this video, but it might be worth researching if you're interested in that. So I want to go into a little bit about the different types of orbits that you can get. Circular orbits are desirable because you can control the speed and it's easy to know the location of the objects. However, the only ones that are possible are the ones that are around the center of the Earth. Now, the orbits that are shown on this right-hand diagram are not possible if you think about the location of the center of mass of the Earth, which will be the center in there. So if we look at this bottom orbit here, the satellite will be attracted towards that center of the Earth, and eventually either the orbit will shift up or it will become unstable. Geostationary satellites are one type of satellite that are always above the same point on the Earth's surface. Due to this, they must rotate in the same direction of the Earth and must be in an equatorial orbit. So due to that equatorial orbit, geostationary satellites, they don't have really good detail around the poles, North and South Pole. To match the speed of the Earth, they have to be really far away in orbit, so the signal strength has to be very high as well. And this causes time delays, such as when you're talking on live TV. Also, by being geostationary and being really far away, the detail of the satellite is limited. So good things about it though, is good for surveillance, so military and weather surveillance, and communications. Fixed equipment on Earth such as relay stations and dishes and antennas that are permanent or semi-permanent, they are fixed to point at that satellite at all times. So these equatorial satellites, they have to be traveling pretty fast to maintain the position that they're looking at and a stable orbit. So because the Earth is spinning, it's advantageous to launch the rocket in a west to east direction to give it a boost, or to give it some of that initial speed that it needs to maintain that orbit. Polar satellites are another type of satellite, and these rotate in a polar orbit, so from north to south, just as shown in the diagram. These are a lot closer to the Earth, and they can orbit the Earth about 14 times a day. So as the Earth rotates below the satellite, so you can picture the Earth's rotation doing this, as the satellite also orbits, it takes an image of a thin strip that it's looking at of the Earth. So the next time the satellite goes around, it'll be looking at the strip that's just slightly to the left of it. And the next time the satellite goes around, because the Earth moved, it'll be looking at another strip. And what happens is the images that the satellite receives, it will just stitch together all these strips and get a complete image.